All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we'll go ahead and get started. First off, good morning. I'm Jason Thomas, Project Engineer with America Makes, and your host for today's OASIS Challenge Informational Webinar. We are very excited to host this challenge in cooperation with the Air Force Research Laboratory and GE Global Research. A few important notes before we kick off the webinar. At the end of the presentation, there will be an opportunity for a question and answer session. And also, if during the presentation you have a question, there are 2 ways to ask your question. You could submit it in the Q&A space on your WebEx screen, and I can ask it to the panel during the presentation. Or you could ask the question directly by raising your hand, using the raise your hand feature to let the host know you would like to ask a question. We will unmute your audio so that you can ask your question, and then we'll mute your audio once the question has been answered. The whole OASIS team is present, so if you have a technical question, now is the time to ask. We will do our best to get all of your questions answered. So today's webinar is an informational webinar for the America Makes OASIS Challenge. The OASIS Challenge is a culmination of America Makes projects, both past and present. Participants will use open source software created in America Makes Project 4039, development and demonstration of open source protocols for powder bed fusion to produce open source scan strategy algorithms. The top chosen scan strategies will then be printed using the M2 Open DMLM machine developed through Project 2030-24, Acceleration of Large Area Additive Manufacturing, also called ALSAM. To tell you more about the OASIS Challenge, it is my pleasure to introduce our presenter, Senior Project Engineer Sean Nesmith from America Makes. Sean, I'll now turn it over to you.
Thanks, Jason. Can you hear me okay?
Sure can.
Thank you. As Jason had mentioned, my name is Sean Nesmith. I'm a Senior Project Engineer at NCDMM. Today, we're going to be discussing the open source additive scanning implementation strategy. From this forward, it's going to be known as the OASIS Challenge webinar. This is a collaboration between AFRL, GE Global Research, and America Makes. Basically, what I'll be doing today is giving you a brief overview of what the challenge is, and then we'll go in a deep dive on how the challenge works. So if you joined us at the TRX, at the summer TRX, this slide will look familiar to you. Basically, what this challenge is, it's leveraging 2 previous projects. The one was an open source software that was developed by GE, and the other one was a current project that's going on, the Acceleration of Large Scale AM, the ALSAM project. What the challenge is, it is a direct challenge to the entire AM industry to advance laser-based powder bed additive manufacturing through the submission of open source computer codes that output laser scan paths with innovative strategies, algorithms, and methods. This is a scan strategy challenge, not a process parameter challenge. As we go through this presentation, you'll see that we actually fix all the process parameters and are only allowing the scan parameters to be adjusted. Submissions for this challenge, all the codes, will open October 1st with a deadline of December 1st, 2020. The code language that will be accepted is Python, Java, C# and C++. This is an open source submission, so all code must be open source, public accessible. What we'll be doing with your code is we will be using it to generate laser scan paths for the geometries that you see here in the upper right. You see 2 lattice cones, different types of lattices. You see what we call a tensile bar, and we also have a different angled nut that you see there. These will be printed out of tie 6.4. We also have a mystery part that we will have part of this challenge. The mystery part you'll see in some of the build plates, you'll see a part there, but that is not the mystery part. That's just a representation of the mystery part. The mystery part is part of the challenge. What you will be given, though, is the base code, which is in C++, and all the models that you see here will be provided to you also. The criteria of interest for us is going to be the code quality, code run speed, along with porosity, tensile strength, ductility, surface finish, and geometric fidelity. There will actually be 2 different evaluations. The first evaluation will be for the code quality. Once we run all the codes through the code quality, we will only select the top codes to move forward and go on to be printed. So that's important to note that not all entrants will be printed. That'll happen around the April 1st timeframe whenever we start printing the build plates. The awards, we are planning to announce awards June 4th, 2021. There are $68,000 in total awards. First place will be $25,500. Second place will be $15,500. Third place will be $10,500. And there'll be 3 honorable mentions of $5,500 each. As Jason has mentioned, if anybody has any questions during this, please, this is the time to ask. Go ahead and do it through the chat, through the Q&A, or raise your hand. The other thing I wanted to mention, everybody, is this will be recorded. It will go out onto the YouTube, but it will be a link on the website, the OASIS website, to that video. And I will be also PDFing this slide presentation and putting it into the GitHub site. If your code does get selected to be printed, you can see the build plate right there. As I mentioned, we printed out a TIE 6.4. You see 2 different build volumes. Block volume 1 is a participant design trophy or medallion. This is where you get to design your own trophy or medallion that you would like to be printed if your code is selected. The block volume size is 60 by 75 by 60 millimeters. But we're limiting the consolidated volume of your medallion or trophy, including the supports, to around 30 cubic centimeters. The part must have features such as holes to allow unfused powder to drain out of the part, and there'll be no post-processing done beyond cutting the part from the plate. We will not be doing any support removal, no polishing, no heat treatment, nothing like that. We are just stress relieving and cutting from the plate. Block volume 2 that you see there is for the mystery part. As I mentioned, there's a part sitting in there, but that is only a representation of the mystery part. The block volume size for that is 70 by 75 by 60 millimeters. It is a representative aerospace component composed of several different geometric features, and we have some of them listed here. Thin walls, thick to thin transitions, various radii, overhanging features, channels, holes of various geometries and in multiple orientations. So that would be the build plate. So to get into the meat of everything, what I want to do is I want to discuss how the challenge works. Basically, you see here, I have 11 different steps. The first 7 steps that are blocked out in the red are required by the contestant. We will go through each one of these step by step. The lower block, which is in the green, is the OASIS team will be doing that. All the code evaluation, the selection of the top codes, print evaluations, and announcement of the winners. All the information that you see in this presentation today is also in the OASIS challenge documentation, which is you can get to from our website. Please read that OASIS challenge documentation. That has all the rules, the complete set of rules and everything for this challenge. What we're doing here in this presentation is basically just going over the highlights. The way I have this set up is you will see step 1 over here on the left, and I will have the title of that step. I have it set up in a way so over here on the right, you can see where we are in the process. So at any time you want to see where we are in the process of steps, I have it listed here. First thing you want to do is you want to go and download the files and file folders from GitHub. In order to do that, you have to go to the OASIS website, which I have listed here. And once this is PDF'd out, you'll be able to click on all these links and they will take you directly to the either the folder location or the files. You want to go halfway down our website and you'll see step 1, step 2, and step 3. Under step 1, download data, you want to click access data on GitHub. You will need a GitHub account in order to do this. Once you get in there, you will see what I have on the right-hand side is the actual file structure. It'll have the baseline source code, all the compiled binaries and examples in it, the license, the OASIS challenge documentation, which I mentioned on the slide previous, and the parts. It will also have a Readme file. The Readme file also has the basic instructions as far as what you need to do to just get going with the challenge. What you'd want to do is you want to clone or download these the files from the GitHub repository. You want to go to the green code that I have circled here in red, and then download a zip file. Once you download that zip file and unzip, All the folders and everything will be there for you. Second step is to review all the documentation. Thoroughly review the OASIS Challenge documentation PDF file. This document contains all the information that you need. If there's anything that you have questions on, please feel free to send us a question at challenge@americanmakes.us. That is at the bottom of the OASIS Challenge website. The deadline for question submission is November 1st, 2020. Also, review all the documentation that is within all the different file folders, all the README files, the doc files, the Excel files. There's a lot of information out there. There's documentation on the source code that is out there, the baseline source code. For the examples, there's a lot of information that you will need to read through and understand for this challenge. Now we get into the good stuff here. Number 3, develop your code, submitted code. As I mentioned, all the code must be open source and public. All private code will be disqualified. So even if your public code, your open source code points to a private code, it will be disqualified. This must all be open source. The submitted code must be one of the 4 languages, C#, C++, Java, or Python. Again, if it's anything other than those 4, it will be disqualified. Submitted code that relies on custom libraries for performing the function that is the intent of the OASIS challenge, such as slicer or scan generation, will be disqualified. But third-party libraries that provide general purpose utilities are allowed. Again, if you have any questions, now's the time. There's a lot of information coming up on the code here. Code license. All submitted code must be clearly labeled and licensed under one of the following open source licenses. BSD2 clause, which is going to be the clause, the license that will be in your private GitHub repository when you go to submit your code. So when you go to submit your code, that license will be pre-populated into your GitHub repository. Apache 2.0 and MIT are also acceptable. If the code is licensed by one of those 2, you're going to need to change that license that is pre-populated. All libraries required to compile and run the code must also be licensed under one of the above licenses. If required, subdirectories of the code may use a different license from the 3 above, but it must be included in that directory. Code directories without a license file inherit the license from the parent directory. System libraries that are part of the Microsoft Windows 10 or Microsoft Windows Server normal installation are allowed for code that is built on Microsoft Windows.
Hey, Sean, we
Yes.
do have a question that has come in.
Okay.
So our question is there a way for individuals to participate? This challenge is too small for many companies, but a good open source developer could likely provide a nice solution.
In order to participate in this challenge, you must be an American Makes member. That's the only thing. Does that answer the question?
I think so, yes. Thank you.
As long as the code's open source and not proprietary to any company, I think it'd be acceptable.
Yes. The participant that the entrant, the organization has to be a member of American Makes in order for a participant to enter the competition. Okay.
Mm-hmm.
Okay, script files. The submitted code must be able to be compiled via a batch file named build.bat or build.sh, which is submitted with the source code. The resulting executable should be in the top level directory. The executable shall reference the input configuration file and geometries from the same directory. 2 additional batch files must be included to execute the compiled code on the 2 different sets of geometries. That would be a run nist.bat for the nist artifact and the run build plate.bat for the build plate. What we're basically doing is when we take your code and do the code evaluation, we're going to be submitting that, running the nist test artifact and the build plate geometries through the code. and we're going to be using that for the evaluation. The NIST test artifact will not be printed. Only the build plate geometries will be printed, but we're using that as a test for the code. So there's 3 things that need to be submitted in here for the script files: your build batch file, your run NIST batch file, and your run build plate batch file. The code should execute as a Windows command line, not as an interactive UI. The output from the program shall be placed into subdirectory as specified by the input configuration file. It shall contain 2 subdirectories, one for layer files and one for scan path files. The layer file subdirectory at a minimum will contain the SVG file output from the program. These will be used for visual inspection of the code output and shall be output at a rate of 1 per 10 layers. This is fixed for the OASIS challenge. The scan file subdirectory will contain 2 folders, one for the SVG output, fixed at 1 per 5 layers, and one for XML output, 1 per layer. The submitted code must create a valid XML and SVG files as defined in the ALSAM multi-laser XML schema document, and that is located out on the GitHub site. Again, you can click and go to those directly.
All right, Sean, we have another question here.
Sure.
Is Linux operating system allowed?
I will turn that over to Mike Tucker and his group.
So actually going to run this via Docker containers. So the Docker containers can run Linux on Windows. So yes, it could be implemented in Windows. And in that case, you should expect to have those build.sh file configured properly to build your code in that platform. There's another slide coming up with more details about how we'll build and run and test.
Okay, thank you very much.
Actually, I think this is the file you were mentioning, Kathy. Mike, you were going to say a few words about this?
Yeah, so thank you. Hello, everyone. This is Michael Tucker. I'm a project leader and a technical teammate over at GE Research. So together with the team, we've been developing the test geometries and the technical backend for this challenge. And for that, I want to make sure that we thank Dave Toledano, who was on earlier. He developed the XML schema that is part of the output file format that we're expecting for this challenge. And also Kathy, who was on just a moment ago, for helping create the Docker workflow for automated code test. So this slide is showing graphically what Sean just said about creating batch files for automatically running the scan path generator. So what we're hoping is that we're just overwhelmed with a number of submissions to this challenge. And in order to be able to evaluate all those, we need to automate the evaluation and running of the code. So for that, what we need from you is a set of batch files that will automatically execute the code on the challenge geometry. Now, those batch files should automatically call the input configuration file. Inside the input configuration file should already have the names of the STL files that are going to be sliced as part of the challenge. All right, so when you execute the batch file, that will call up a command line for execution, which will launch the executable file. The executable file that's going to start generating different types of files as output, or at least we expect it will. So that's going to go into the output directory. Output directory is going to be specified in the input configuration file. So in this example, this folder for the NIST plate would be placed in the NIST plate baseline subdirectory. So inside of there, we are expecting 2 subdirectories, layer files and scan files. So files related to layers from the first slicing of the part, those would go into the layer file directory. And as mentioned, we are expecting SVG output. So those would be scalable vector graphics. And these will be used for visual inspection of the scan paths to make sure that your code appears to be producing valid output. Now, the SVG output we recognize does consume a fair amount of processing time So that's why we want to make sure that it's there for visual inspection, but we also don't want to overwhelm the processor. So we're fixing that for this challenge at a rate of 1 file per 10 layers, and we will do some spot checks on those to make sure that the part is being sliced. All right, optional output for the layer files, or I guess suggested output, would be in the form of XML files. So when you download the baseline code from GitHub, this is how the code is structured, is it generates XML files that describe the outline of each layer slice. Those get returned to the executable file, and then the executable produces scan files. So 2 types of output for the scan file. So one is, again, support vector graphics for visual inspection. This time we're setting it at 1 file for every 5 layers. And then the second, the most important output, is the XML output. So this is the file that describes exactly how the scan path should look for every single layer. So 1 file per layer, and the format must strictly conform to the XML schema. Ultimately, for the code that is selected to be built on the Concept Laser M2, we will be running exactly that code on the machine. Now, the baseline code, as a final step, zips the file, and it's the zip file that ultimately gets transmitted to the machine. But for the purposes of the challenge, zipping is kind of irrelevant to code performance, so we've turned that off by default for the purpose of the challenge. Okay, thank you.
Thanks, Mike. Jason, were there any questions on that?
No, we haven't gotten any in.
Okay. All right. Code will be compiled using Docker containers. The entrants may provide a Docker file to use for building their executable with the Docker build and run commands in their script. If a Docker file is not provided, then the following images in table 1 below that you see here will be used to build the entries. So depending on what code language you select, this is how the Docker file will be built if it's not already within your script. This is all inside of the OASIS documentation. You can find this. The Readme file. All code submissions must include a Readme file describing how to build and run the submitted code. It must also state any custom libraries that the submitted code uses. Basically, we want to use this file as, okay, once you submit everything to us, how do we get this up and running? We want to make sure that we're following exactly what we need to follow, so we don't inadvertently do something that we shouldn't be doing with your code. So that's very important that you supply a Readme file. The virtual target machine that will be running the code is a Microsoft Server 2019 operating system using Docker containers. They'll have 2 virtual CPUs, Intel Xeon CPU, E5-2673 version 4. The important thing to note here, though, is only 1 CPU will be dedicated to the program execution, so it'll be a single thread. 2.3 gigahertz, 64-bit OS, 64 base processor, and 4 gigabytes of RAM. So what I really want you to take away from this slide is that only 1 CPU will be used. Next step, step 4, is complete the build parameter files. You heard Mike Tucker talk about some of that briefly. 2 pre-filled configuration files are provided as part of the baseline source code for the 2 code evaluations. The 2 code evaluations are the NIST test artifact and the build plate. If you run the base code with what we currently have out there in the GitHub repository, the code will run and it'll give you scan strategies from that. But what we're looking for is different ways, new ingenious algorithms or anything like that to enhance this. The NIST plate baseline is configured to run the scan path generator on the NIST test artifact geometry, and the build plate baseline is configured to run the challenge geometries. The build plate baseline contains placeholder and the user's defined trophy medallion part. Another thing you want to review is the OASIS allowable build parameter ranges PDF file. This file will tell you what can be changed and what cannot be changed within your config files. Anything that is adjustable to the participant will be is not grayed out. If it's grayed out, you are not able to change it, it is fixed. You also see that within the config file, and I have examples here. If you look this one in the middle, you can see that everything is black, nothing is grayed out there. Those are adjustable scan strategy parameters. If you look to the lower right, you see fixed process parameters. They are grayed out. Those are fixed for the challenge and cannot be changed. Again, all process parameters are fixed. The only thing that is adjustable is the scan strategy parameters. One thing to keep in mind is that your scan strategy may require more parameters than what is provided by the baseline configuration file. You can add additional parameters to the configuration file, but do not remove any of the existing parameters that are shown there. This is inside the build plate baseline configuration file. Be sure that when you create your medallion or trophy, that you change the user choice part bounding box.stl to the name of whatever your medallion or trophy is. You want to make sure you replace it within here on tab 6 under parts. You also want to enter in the position offsets X, Y, and Z. We'll be explaining that a little further when we go into what the medallion and trophy can be. Number 5, design your own trophy or medallion. A designed trophy or medallion submitted by a participant will be printed if the submitted code is selected for printing. The file type can be binary or ASCII. It has to be an STL. Please dimension your part in millimeters. The max file size can be 100 megabytes. The volume bounding size is 60 millimeters by 75 millimeters by 60 millimeters. And we show within the build plate that here in the geometry, you can see the X, Y, and Z. The part must be located inside the highlighted volume in the drawing user choice part bounding box.pdf. You must note the center point, which is included in that challenge geometry. You can get that by exporting the STL file with the same coordinates as the build plate or applying the X, Y, and Z offsets to the STL file in the input configuration file. Consolidated volume, including the supports, that's important, is limited to 30 cubic centimeters. This is just a little over 10% of the bounding volume. If it is larger than that, we will not print the medallion or the trophy. The designed trophy or medallion must have features to allow unfused powder to drain out and supports if required. We will not be adding any supports or anything to your design, so everything must be in there. There will be no post-processing, as I mentioned earlier, beyond stress relieving, cutting the part from the plate. So no support removal, no polishing, and no heat treatment. You will basically get the trophy or medallion as we just cut it off the plate. No additional modifications, scaling, positioning, support geometries, or repair will be done by the OASIS team to the STL file. It's strongly recommended that the participants confirm that their STL files are well formatted and that their code will produce valid outputs for the submitted part. If the designed trophy or medallion do not fit within a volume bounding size, or the consolidated volume is larger than specified, it will not be printed. Now to enter the contest, again, you will want to go to our website and scroll a little over halfway down, and you'll want to go to step 3. There, right now, you do not see a submit button, but there will be a submit button added on October 1st, 2020. That's when we'll start accepting submissions. The deadline for submissions will be Tuesday, December 1st, 2020 at midnight. Submissions received after that deadline will not be considered. Participants will have to answer a few questions and then receive a link to a private GitHub repository where they will submit their content. After the deadline, that private repository will be switched to public, and all the participant access will be removed until judging is complete. So basically, you can upload and use your GitHub repository from October 1st to December 1st. But after midnight of December 1st, we're shutting it down and we're switching it over to public. So nobody will be able to see your code until after we switch it over to public. Step 7, upload submissions to private GitHub repository. You can update your GitHub repository with your code, trophy, medallion design, and completed build parameter files at any time. You can also revise them, clear up to the December 1st deadline. One submission per entry though. If you want to do multiple entries, you will have to go in and create multiple site repositories. One entry must include the submitted code, the code license, the script files. There's 3 of those. That's the batch file, and then the run NIST batch file, and then the run base build batch file. You got to have the Readme file, the build parameter files, one for the NIST plate and one for the build plate, and the trophy and medallion STL file. At that point, it turns over to the OASIS team. We'll begin the code evaluation. All ties from the code evaluation will be decided by the code run speed. What I have here in front of you right now is how we will be evaluating the code. There'll be 2 different ways. We'll be evaluating the code quality and the code run speed. With the code quality, we'll be looking at vulnerabilities, bugs, code smells, and security hotspots. This will be done using Sonar Cube. This is 50% of the total score, and the scoring is weighted 50% for bugs, 25% for vulnerabilities, 15% for security hotspots, and 10% for code smells. How we're scoring this is it will be normalized, weighted score based on an evaluation from Sonar Cloud IO using default rules and estimate of effort to remediation. Basically, what Sonar is doing is they are going to take your code, run it through their software, and tell us how many bugs, how many vulnerabilities, code smells, what's all coming out of that. And then they put a time, an estimated time of how long it would take to remediate those bug vulnerabilities. That's what we're going to be using to evaluate the code quality. The code run speed is going to be the total time it takes to create a valid XML and SVG files for the NIST artifact and a build plate. This does not include your trophy or medallion. We will not have that in there. The runtime on the virtual machine using the Microsoft Server 2019 operating system with the Docker containers. Again, single core, single threaded. This is 50% of the score. Runtimes longer than 6 hours will be disqualified. So make sure that your runtimes are less than 6 hours. Again, any ties on the code quality will be decided by the code run speed. The rules for assessing the code for SonarCube can be found at rules.sonarsource.com. What you want to do is navigate to your appropriate language that you are writing your code in, and you will see the rules for that on how they're going to evaluate the code. One important thing to note, though, is different code languages will have different rules, which may impact the scoring of different projects. So you may want to take a look at that and how it's being scored. Sonar's analysis includes an estimate of the amount of time required to remediate a given issue, which is a proxy for the complexity of the remediation effort. These estimated remediation times will be used as a basis for calculating the score with a perfect entry having no issues. The classification of the issues will impact the weight applied to the time estimate. For instance, the time to remediate bugs will contribute 50% of the code quality score, while code smells will contribute 10%. So what I have below there, what I received from Kathy, is actually some example of scoring. What you can see is let's look at project B. You can see that the bugs are 1.2 and the code smells are 2.083. So the overall score is around 49. But the code smells are more for project D, but the bugs are way less. So that's why it's showing a higher score for project D. So you really got to look at how these are being weighted and what you're going to target and go after in your code. Were there any questions on that, Jason?
No, so far so good.
Okay. Once we go through the code evaluation, the top selected codes will be sent for print. Again, not all codes will be sent. It will only be the top selected codes. They will be sent to GE Global Research for the build plate to be printed using TIE 6.4 on the Concept Laser M2 Open Direct Metal Laser Melting Machine. The print will include 4 tensile bars, 2 angled nuts, the 2 lattice cones, the participant design trophy or medallion, and the mystery part. You can see them here on the build plate as are shown. The mystery part is a representative aerospace component defined by the OASIS team composed of several geometric features, including thin walls, thick and thin transitions, various radii, small overhanging features, channel holes of various geometries and multiple orientations. The volume bounding size is 70 by 75 by 60 millimeters. The mystery part, the height is a little over 44 millimeters. The volume of it is around 40,000. The surface area, a little over 60,000 millimeters squared. The performance of all code entries will be evaluated using the same mystery part along with the other geometries on build plate. We're not going to release any other information on the mystery part until after the judging is complete. So again, you see a representation in the build plate geometry here, but that is not what's going to be built. Once the build plates are done, we will then do a print evaluation. The build plate will be stress relieved and parts will be cut from the plate using a wire EDM. No further processing will be done to the parts. The first part that we will look at are the angled nuts. There will be 1 angled nut left whole and 1 angled nut will be cross-sectioned. The angled nut that will be cross-sectioned at notches that we have in the geometry. Whenever you look at the geometry, you'll see some notches in the center of the nut. That is where it will be cross-sectioned. The nut will go through 3 different reviews, the surface finish, geometric fidelity, and the porosity. First, we'll look at the surface finish here. There will be 24 measurements. We'll be looking at surface roughness, SA, with a profilometer. 1 unsectioned nut, 8 total surfaces will be evaluated. So you're going to have the sides, the top, and the angles, but it does not include the cut mounted surface. So when we cut it off the plate, we do not look at that. The score percentage is going to be 25%. You can see how the element is scored there. The average roughness will be used in the scoring. For geometric fidelity, we're going to be using an unsectioned nut and a section nut. 8 surfaces will be looked at and the hole size on the unsectioned nut. On the section nut, though, we'll be looking at the hole size. That'll be done with an optical CMM. That's going to be 35% of the score. The position of the EDM cut to remove the nuts from the build plate will not affect the geometric fidelity. So if we're off a little bit on that, cutting that from the plate, it does not affect that. Average deviation will be used in this scoring. Finally, on the nut will be the porosity. This will be done on the cross-section nut. The cross-section nut will be mounted, polished, and photographed across the entire surface. Bulk porosity, near surface porosity, and total porosity will be recorded. Any pores smaller than 5 microns will be ignored. This will be done on an image J. 40% of the score. Let's see here. Upper limits of the porosity is 10%. Anything more than 10% will receive a score of 0. So if we look at it and there's more than 10%, it's an automatic 0 on the score. Next, we'll look at the tensile bars. There'll be 2 evaluations on the tensile bars, ultimate tensile strength and strain. Note, all 4 tensile bars will be machined into miniature tensile specimens and tested. They will be machined to a surface roughness of 32 microinches. They'll be tested on an Instron tensile tester. Each of them are 50% on the score percentage. The average of the best 3 out of the 4 results will be used in scoring. So the worst result will be thrown out. That is for both the tensile strength and the strain. The lattice cones. Now the lattice cones will not be cut from the plate immediately, because what we're going to do with the lattice cones is we are going to measure with calipers the height to the first lattice failure. And that's how we're going to get a score on that. So this will be done prior to removal from the build plate. Those are both 50% also on the score percentage. Once we have all the evaluations completed and we tally up all the scores, the announcements for the OASIS Challenge Awards are anticipated to be done by Friday, June 4th, 2021. A workshop will be held for the winners to showcase their code. Important thing to note here, though, is the award checks will be written to the American Makes member organization, not to the individual. No award money under this challenge can be paid to non-U.S. citizens from China, Iran, Iraq, Syria, Sudan, North Korea, Cuba, or Venezuela. That's very important to note. The awards, as I mentioned earlier, are shown there. There'll be a first, second, and third place, and there'll be 3 honorable mentions.
All right, Sean, we have a question that's come in.
Okay.
Scan strategy depends on the build material. What are the allowable methods for taking into account the build material?
Mike, are you there?
There's only going to be one material used for all the parts. Is that correct?
Yes, tie 6-4.
Yeah, so what we're doing is we're providing a set of parameters that should be pretty robust and pretty reliable for the material and for the layer thickness that we're building in. And on top of that, the baseline code that we're providing can already provide scan paths that should work with that material. Now, by scan strategy, you could think of this different ways. It's what path does the laser beam follow as it traverses across the entire surface of the plate? Now, you could imagine the baseline code right now, it basically draws straight lines from one edge of the plate to the other edge of the plate, and wherever it intersects with a part, it turns the laser on and off. Okay, so it's very rudimentary. It's effective, but it's rudimentary. So now you could imagine different ways you can cover the area across the build plate. So you could think of checkerboard patterns or space filling curves, or coming up with different ways that you can move the laser from one region of the plate or one region of the part to another region of the part, and by thus controlling the delay between one pass of the laser to the next, you can affect the part properties in the end. So that's really the focus of this challenge. It's not so much on the parameters, that's why we fixed those, but really how do you guide the beam over the plate to cover the cross-sectional area of the part at each layer.
Good, thanks, Mike. Any other questions, Jason?
Nope, no more right now.
Okay. As far as eligibility, I mentioned this a little bit earlier. Domestic and foreign members who are in good standing with American Makes are eligible to participate. Only the lead proposer must be a member of American Makes. Participants of the lead proposer's team can be made up of American Makes members and non-members. If the lead proposing organization is not currently an American Makes member, the organization must become one by December 1st, 2020. Information on how to join is available here at the membership page. Again, you can click on this once I output the PDF off the GitHub site. One important thing to note, though, is foreign membership approval process requires a minimum of 3 weeks to complete. So you don't want to start that around Thanksgiving. It won't happen. I'm Members associated with NCMA, FRL, and GE are not eligible to participate in this. Any questions regarding the challenge at any time, as I mentioned, can be submitted to challenge@americanmakes.us. That is at the bottom of the OASIS Challenge website. What we're going to be doing is we're going to be making a list of frequently asked questions and answers at the bottom of the website so that people can go down and see what has been asked and how it's been answered. Even the questions that we have here today, I'm going to be going back through this. We will be listing those out on the website. As far as reasons for disqualification, just to briefly go over this, I have some reasons here listed. If the participant is not an American Makes member by the time that I had mentioned, that would be for disqualification. Not all the required files are submitted by December 1st. If the submitted code is private and not open source. If the submitted code relies on external libraries to perform the key elements of the challenge, as I mentioned, that slicer, if it relies on that, it will be disqualified. Submitted code that is not written in one of the 4 languages, the C#, C++, Python, or Java. Submitted code cannot be compiled. That'll be a reason for disqualification. If the submitted code does not create valid XML or SVG files. If the submitted code takes longer than 6 hours to run or crashes during evaluation. This is with and without the trophy. Created files causes the print machine to crash, including the trophy. That will be a reason for disqualification. Any submitted code that is identified as malicious software will not be run. Proper license must be stated within the different directories. If the proper licensing is not associated with the code, then it's a reason for disqualification. So that, I think that's where I have everything wrapped up. Jason, if you want to, you can unmute everybody and see if there's any questions that anybody has. Now's the time to ask. We have the panel of the OASIS team here. So feel free to ask us any questions that you have.
Okay, so as I do that, there is a question that came in, so I'll just ask that of you now.
Okay.
Is there an API to interface a new method with existing code?
Yeah, so we've provided a set of code that works as a baseline, and the code that we provided, so walking you through how it works. So first it makes a call to the open source slicer program, so a compiled version of that code. So that's what slices the part into individual layers, and that's followed by a call to the scan path generator that Dave has been working on. And that's what lays down contours and hatches on top of the build plate. So as far as an API, I can't really say that you could use it as an API. It's really just entirely open source in that you can take the code as it's been delivered and modify it however you wish to do so. So Slicer, for example, is a piece of code that's borrowed. It's open source. And you can go ahead and use the tools and functionalities associated with that. But as far as the rest of the baseline code, I guess I wouldn't say that there's an SDK associated with it, but you can develop whatever you want from scratch around that.
I just want to add one point. The baseline code is actually built with Microsoft Visual Studio, and that is not how we plan to build the code during the challenge. We'll be using GCC compiler, so you may need to modify the baseline code to work with that.
All right, thank you. So any attendees that would like to ask a question, I have unmuted, so you can control how you're, how you unmute yourself. If you have any questions, you can go ahead and ask them now.
So are you saying that if I wanted to change the number of contours or the type of contours or whatever I feel is suitable for the part, then I could specify that? Is that or any other strategy that I'm doing? I can I can use that with the existing code, like calling functions with the existing code, or do I have to write everything from scratch?
So that, with the functionality you described with just doing contours and hatches, that is already enabled in the baseline code set. Now, where you would modify that is in the input configuration file. So far, those are all Excel-based. So you can open up the Excel file, and Sean was showing which cells are grayed out and which cells are black. So the black cells are ones that you can edit, and that includes contours and hatching. So everything, it's too small to read here, but in that left panel, there's a whole lot of settings related to contours and hatching, and those are freely editable. So you can change the spacing, you can change the number of contours and the number of hatches. But keep in mind that just changing the parameters in the table is not completely in the spirit of the challenge. We really want to see material changes to the code and to the scan paths themselves. So, yep, that's what we're looking for.
This is Dave, who developed the baseline code. Right now, the baseline code applies a single scan strategy to the entire part. So if you say I want hatches spaced 75 microns apart and 2 contours, the whole part gets that regardless of geometry. So what we're looking for in the challenge is to take that and become more sophisticated. Maybe I'll put into the Excel spreadsheet that I have 10 scan strategies, and I will select between them. Different areas of the part get scan strategy A versus B based on whatever thickness, overhang, or some other criteria compared to the baseline, which will just apply the same strategy blindly.
Thank you.
Any other questions?
Sean, have we talked about how other questions will be handled as they come in during the challenge and how they're posted back for everyone to see?
Yeah, they will be, we talked about that at the end here. The questions will be added to the bottom of the American Makes website. So any question that comes in, it will be answered by someone on a team. It'll be directly answered, and then it will be put on the website.
I guess my question about the API was that, when you write a new code, the new code will generate your internal scan strategy, but somehow that needs to blend or be consistent with what is existing with respect to, if, for example, one is to say that I have a baseline code that's generating the scans in a particular way, and I want to change something which is in a certain part of the layer, then whatever the new method we use to generate somehow needs to blend in with the existing scan strategy. And I was just wondering that, are there mechanisms by which one could blend such things, are there, or do we just kind of, just figure it out how that all happens?
I think Dave can explain more about how the mechanics of the baseline code are. But my understanding is from each slice of a layer, you have just a contour representing the outer perimeter of the part and any internal contours representing any internal features or geometry. And the code right now, it basically runs from one edge of the part directly to the other edge of the part without doing any feature recognition beyond just recognizing the part boundaries in each slice. Now, this would be an interesting part that we would hope that someone would develop, is some way to interpret the features built into the geometry and vary the scan path about that. So Dave, do you have any thoughts on that?
Yeah, you said it right. The baseline code looks at contours that are given and applies one scan strategy in between, essentially colors within the lines. What someone could do is break up a given region into subregions and submit those to the right portion of the baseline code and let it color in the numbers with, say, color key 1 or 2, depending how you do it. But I think what has to happen is that segregation within the region, which the baseline code doesn't do. Otherwise, we don't have to set it up as an API, but the source code is documented as to what it takes in for a region. Maybe I could document that further as well, because that's a good point. Where would you put something in if you have a new region versus the ones that are given?
Okay, did that answer your question?
Yeah, I think so. We have to kind of.
Okay, and
yeah, I do understand your
go ahead.
point, though. It's a good point, because if we had set it up as an API, you could say, I want to use scan strategy number 3 on a layer defined by this bounding box or this contour that I've now created. That would be easier for you. I'm just going to accept that.
Okay. Okay.
Yeah. But basically, it's looking for contours that are in basically a line format, and it'll color within the lines based on that.
Okay.
Okay, are there any more questions for the team? All right, if not, that will wrap up today's OASIS Challenge informational webinar. I would like to thank the OASIS Challenge team and everyone else who has joined us today. If you have any further questions for the team, please send them via email to the challenge@americamakes.us, and the answer will be posted to the America Makes website at americamakes.us/OASIS. Thank you very much, everyone. Have a great day, and we hope to see your challenge submissions. Thank you very much.
Thanks, everybody.
Thanks.
Thank you.